So welcome back to Adventures in Blockchain. This is the podcast that's all about blockchain technology. So I'm Gregory from Dapp University, and I've got my co-panelists Bruno and Roman here today to talk about how blockchains work. So hey guys, excited to do another episode.
Hi Gregory. Hello everyone.
Yeah, awesome. Well, cool guys. Well, today, we're going to cover this topic of, how does a blockchain work? And this is a really common question that newcomers into the space have, just because it's such a paradigm shift. It's a new piece of technology that seems to just, work differently from other things that you might have encountered in the past. So, Roman, you want to kick us off and kind of talk about, why we need blockchains in the first place? I mean, one of the biggest use cases that we have for blockchain right now is payments and solving some of the problems with payments. So you want to tell us a little bit about, what that looks like, what advantage a blockchain gives us in the payment world?
Sure. So before we talk about how does a blockchain work, I think we should ask ourselves, how does our current technology work for processing our payments? For example, how does a PayPal, Stripe, or Venmo work at all? So basically,
sure, yeah, that'd be great.
The first step, we open up an account. Where does the account live? It lives in some sort of central database that PayPal or Venmo holds. And they basically store all the information of my account, of my current balance, and of a list of all my transactions that I've made too. And basically, when I open a Venmo account, they tell me, okay, can you fund your balance with some other banking solution or some other payment processor? What they essentially do, they record that balance into their database so that I can spend my balance in the future. So what we just explained, like how does the central system works comparing to blockchain. And blockchain has a sort of similar processes, like similar objects, I would say, like account object, transaction object, your balance. And the central solutions, basically, they are responsible for making sure you cannot do a double spend transaction. That's why it's efficient, because we have to trust them that they'll make sure you can't just print money.
Right.
With blockchains, what's very fascinating about blockchains is it solves the problem of double spend without.
So what does that mean? What do you mean by double spend?
Double spend means if I have $10 on my account, I can spend this $10 twice. So I can send $10 to Gregory and $10 to Bruno. That's basically a double spend problem.
Right.
I should only be able to spend $10 once.
And essentially, that's a problem inside of a database, because if the database just tracks that you have $10, that could potentially be manipulated, right?
Right. With the central authorities, they can go to the database because only they have the accounts. And we, as the customers of PayPal or Venmo, we don't have this access. We don't know what's going on behind the scenes exactly. And we can just look at our data and they sort of allow this for privacy reasons as well. I can just look someone else's account and see what kind of transaction he made. I think it may be possible with Venmo, but I'm not sure about PayPal.
Mm-hmm. So what you're saying is that the main thing about transactions and payments is that today it revolves a lot around trust. We have to trust our banks or our operators that, the money that I have is actually going to be sent to who I have to pay, or that I actually have the money to begin with. And, how does the blockchain solve that? How does the blockchain approach that?
So I think the really good question would be, can they change the data? Yes, they can, in terms of central payment solutions. With a blockchain, nobody can. That's the most powerful answer why blockchain is there. So what I mean by that, when you create a transaction on the blockchain and this transaction is valid, and it's been accepted by the miners and included into this sort of decentralized database, that means nobody can ever reverse the transactions, period. It's completely immutable, and it's already validated this transaction that it's not a double spend transaction. And there are mathematical and cryptographical algorithms that are being used to make sure the blockchain, this like particular blockchain, can be trusted. Mm-hmm. There are some sort of other blockchains that some people say that it's centralized, or there is like an easier barrier to manipulate the transactions, to manipulate the balances. Theoretically, yes, it's possible to execute a double spend attack. It's also called like double spend attack could be a little bit different than 51% attack, but essentially with a 50. I'm sorry, I'm getting into many technical details. So 51% attack could be used as a double spend attack. What 51% attack means is that if you have more than 51% of the computation power in a proof of work algorithm, you can execute a double spend.
Sure. Yeah, totally. Yeah, that's pretty crazy. So yeah, thanks for that explanation, Roman. I mean, that really shows us a huge benefit of the blockchain over these traditional payment processors and financial transactions and payments. So maybe let's talk about this as a use case to understand how the blockchain works as a solution, as a technical solution, and the mechanism behind it. So whenever I talk to people who are new to blockchain, I try to help them think about it in terms of things that they're already kind of used to, at least developers or other people who have some technical knowledge, which is I kind of think about the blockchain fundamentally as a database, but also fundamentally like as a network, kind of all in one. Because, it's something that you can connect to, store information on. It's responsible for maintaining a ledger. And that ledger can be used for lots of different use cases. But the ledger here that we're talking about has a pretty clear application to financial transactions, because that's essentially what accounting really is all about, is a ledger system. You have an account on the blockchain, and your current balance is made up of the history of all your transactions within that account. If you funded it for the first time, then your balance is just the sum of that single positive transaction, that credit to your account. And everything else, tied to your account is just the sum of taking money out or putting money in. And that's the history of the financial transactions that we're talking about. And we can maybe use that model to understand how the blockchain facilitates all this and makes this possible. What do you guys say? Does that work?
Yeah, I think that something about the blockchain technology that to me is the most fascinating point of it is that if you think about the financial transactions that we have today, it's like I said, it's basically a trust system where one party it's like a third party or something like that intermediates our transactions, and they keep a ledger, a central database stating, okay, this was transaction number 1, transaction number 2. Bruno has $100 that he's going to send to Gregory, and that's transaction number 3. And all of those records are kept in the bank ledger, for example. With the blockchain, with a blockchain, what you have is, like you said, Gregory, it's more of a network of everyone has a copy of that ledger, and there is no regulatory position. There is no party that says, okay, this is the truth, and if you don't think this is the truth, well, deal with it. The truth becomes available from everyone's perspective. So like Roman said, with the 51% attack, that's the that's when you sort of convince 51% of the network that a specific ledger with a broken record, for example, or like a double spending record, that is the truth. And then if you can achieve that, then yes, you can achieve a double spend record. But if you think about open blockchains such as Bitcoin or Ethereum or whatever, the computational power for you to be able to do that is so big that you wouldn't be able to, it would be too expensive in comparison to what you could get back from that. So to me, the magic of blockchain is, figuring out, like, having that network where the word of every single member of the network is, part of what the truth actually is. And in the financial situation that we have, the use case that we have, that is really, what makes the transactions work. And, we can say, okay, this transaction was made. And then if Gregory says that transaction was also made, between the three of us, if the three of us are a network, I say that a transaction 1 is valid and Gregory says that transaction 1 is valid, then we're majority in the network. So then that transaction gets validated, and that's the consensus that's achieving consensus in the network. And there's a lot of algorithms to achieve that consensus. It's different for private and public blockchains and whatever. But the main thing is achieving that consensus and keeping track of the ledger between the entire network and not just a single member deciding if transactions are valid or not.
Yeah, totally. And before we get too far into the technical details of some of these things, I kind of want to draw us back into maybe some fundamental questions people might have, right? Which is, how is it, and you're already answering some of these questions, but I want to kind of clarify it, which is, why is it safe to put financial transactions out there in the public? How does it actually secure to do that with a blockchain, and how is this a good alternative? And also, these use cases that allow this, you talk about public blockchains, that's something that's different from private blockchains. There's a lot of vocabulary words kind of inside of here that we need to unpack a little bit. Mm-hmm. So maybe, Roman, you want to kind of weigh in on why it's okay to put financial transactions in the public and for lots of people to hold the record of these transactions, and how that works as an alternative to these centralized systems.
To me, the benefit of using the blockchain transactions is that I know no one can censor my accounts and no one can put any sort of geofencing, or let's say I used to have Visa credit card that was issued to me as a Russian citizen, and when I came to the United States, I wasn't able to use it because they say, yeah, we just don't want you to use it there. So with a blockchain, there is
right.
there are no requirements like how old are you, or what's your state, where you located at, or it's just usable. And you're even if you're 5-year-old, you can have your own account and start making payments and running your own business or anything like that. To me, it's really, really fascinating. And if you're asking me if there is any privacy issue, yes, definitely. Right now, with the open public networks, it's a little bit hard to run a business because every transaction is public and competitors are looking at your transactions. For example, I run a D app that is called Multisender, that app. And what I see what my competitors do, they look at all of my transactions of my customers, and they go to their customers and say, okay, don't use the Romans tool, use my tool, it's better. So that's a little bit of issue of running a business on a public blockchains. And I think when the combination of private transactions will be merged with a public blockchains, that would be detonating power,
yeah, totally.
Emergence of the booming business for the all blockchains. As a personal transaction, not just a business, I feel totally safe. If somebody looks where I send the money, because technically they can see the account as who received the money, but they don't know who that person is. unless they will run some sort of analytical data, and there are already companies that can analyze the data and can identify an account using some sort of public information from ICOs or crypto exchanges to match your identity with your accounts in blockchain.
Yeah, because that's something on the public blockchains as well, or even every blockchain, is that you need to have a wallet, right? Which is your address or your ID, if you think about a conventional database. And like you said, the wallet itself, it doesn't carry any information about, who you are and who's the owner of the wallet. It's just, a bunch of numbers that say, okay, it's sort of like your IP address. It's your identification. And when you transact something, you're sending, those valuables, coins or whatever between those wallets. And you don't know if, okay, Roman is sending something to Bruno. It's actually like Roman's wallet ID number 123 is sending, something to Bruno's wallet ID 324. And the way that they can, track you is with those currency exchanges or crypto exchanges, those agencies that you can go to buy cryptocurrencies. And that's when, hackers and whatever, they can, identify who's the owner of what wallet. Is that correct?
Yes, that's correct. I think it's mostly used for, government agencies for, getting the data of bad people. And with a single request, I'm pretty sure they have pretty much figured it out to identify the accounts and find the people behind the blockchain accounts.
Mm-hmm. Awesome. It's sort of a little bit like, it reminds me of, when there was that Silk Road investigation going on, where people said, okay, the dark web or whatever, it's completely anonymous, and then people found who the owners of their addresses were, and it's never 100% anonymous. There are ways of identifying who is the owner of certain wallet or something like that. But in the concept, if we apply the concept of blockchain 100%, it's just transactions between wallets, between addresses. And doesn't that make it a little bit dangerous? Say I have a wallet, for example, I have my ID and my password for my wallet, but doesn't that make it kind of easy for me to lose that wallet, or for someone to grab that wallet from me? What do you guys say about that?
With a great power becomes greater responsibility. Yeah, you are the owner of your money, and in a blockchain world, you should forget about something like, I forgot my password or I forgot my ID. Who should I email? Mm-hmm. You cannot email anyone. We have this big problem right now in blockchain world, that people are really, really used to those old traditional financial systems, and they lose money, they lose accounts, they lose private keys, their seed phrase, and they are trying to contact someone like, hey, who can help me with that? Like, I need to get access to my account. Well, you can't. You have to educate yourself that this is the new world, these are the new rules, and if you want to really if you really want to hold your money, not to delegate your money to some agency, you should be able to learn how to protect yourself and learn some measures about security. But I understand it's really, really hard for non-technical people. So I think right now there are companies and solutions that are working really, really hard on it to simplify the process and provide some unique solutions, like Vault12.com. They're working on some really cool algorithm to secure the accounts using like a social security. I mean, not the social security in concept of the United States social security. Social security meaning I can delegate I can split my private key into like multiple parts and send these parts to my friends and family. So if I'm being hacked, I can retrieve my secure data using those small pieces. At the same time, they cannot collect all the pieces by themselves if they want to, steal my money. Essentially, that's some of the cryptographic algorithms out there that exist right now, and people are building user interfaces to allow the new experiences to enable greater security of their accounts.
Yeah, because like you said, in terms of user experience, in order to get invested in cryptocurrencies and, really dig into blockchain, it can be a little overwhelming for your average person, not, non-technical people, because if you're going into blockchain and you're going through an agency or something like that, it doesn't make it that much more different for someone that doesn't know that it is actually blockchain. The main thing is when something happens, you don't really have anyone to go to, and that could be really scary for some people. And I think the main reason why me personally, I didn't get invested into cryptocurrencies right now is that, the security is on my end, not necessarily that, but, I have to hold my wallet. I have to protect my password. And I know there's a lot of gadgets that you can buy or, a lot of things that you can do to protect your wallet and everything. But even to me, that I am a technical person, it sounds a bit overwhelming to, actually have to take such good care of my money. And like you said, there's a few parties trying to, make that a little bit easier for everyone. But in a long-term basis, do you guys think that there will be a solution for that? Do you think we're evolving towards that or something?
Totally, yes. I am totally bullish on the better ways to achieve how to store your seed phrases and private keys. And I think just as a little conclusion to this topic, I think when you think about blockchain and keys and something like sensitive security information, you should think it as your cash money. If you have your cash money in your pocket, you have it. If you lose it, it's gone.
That's a great analogy, yeah.
Right. And if you lose your cash, you can ask someone, hey, where is my cash?
Yeah, it's not like you can just, in a park or something, you see cash lying on the floor and you say, okay, who's this $50 bill or something like that? And everyone's going to come running to it, of course.
Yeah, everybody will grab it and take it. That's it.
Yeah, I think that's a great analogy, Roman. So, kind of maybe building off that and, trying to answer this question maybe from a technical perspective of how the blockchain works. We talked about your account is something that you have ownership over, and the network is sort of responsible for, holding all the transactions and telling us what your account balance is, how much cash you have, to your point, Roman. Tell me a little bit about, or we'll just talk a little bit about, cryptography in this, maybe getting a little more technical. The term is that we came up with initially as cryptocurrency, right? And cryptography's got several different roles in this mechanism of creating a currency. So maybe let's talk about how the transactions are actually secure, like why it's safe for this to be on a public ledger where everybody's got to copy the data. Like we talked about that 51% attack earlier. Maybe we'll get there and talk about what that is in detail, but why is it safe? Why is it highly unlikely that these this transaction history is going to change.
Mm-hmm. I think that the main point for that is the consensus algorithms. But to explain it in a deeper way, you have to think about the blockchain itself. Like, what is it? It's basically an entire ledger, a book of records that is going to tell you, okay, you have one block is, say, I don't know, 5 transactions or 10 transactions are stored in a block, and every single block is connected to each other. And those blocks, they're generated, like, say, every 5 transactions, you generate a new block, right?
Yeah. So whenever I explain this to people, I try to clarify, the blockchain fundamentally is comprised of transactions or records, like in a database. And these transactions or records are grouped together into bundles of records called blocks, which are chained together to make up the blockchain.
Yeah, exactly. And the way that all of that works is always in a cryptographic manner. So every transaction, they have a cryptographic signature on it, and it can vary depending on what algorithm you use or what's the implementation of your blockchain. But on Bitcoin, I think they use SHA-256 or SHA-256, the algorithm to create hashes, fixed length hashes, and every transaction creates those hashes, and those hashes in their each transaction, and then in turn they create those blocks, or they're grouped together, and each block can be represented by a hash as well. And the way they're linked together is sort of like, they call it a Merkle tree. So if you think that block 1 and block 2, they're connected together, they create a single hash. So block 1 is a hash, block 2 is another hash, and the translation of block 1 plus block 2 equals another hash, and all of the hashes, they're fixed in length, and they can be translated into data. So the way they're connected to each other is creating that other data, and you create a Merkle tree by having every single block, coming down to a single hash. You can translate the entire ledger in one single hash. And if you change anything on the data, even if you add a comma or if you change a character or whatever, the hash changes completely. So that's how you know that, okay, I have hash 123 and I know it's a valid hash, but then something changed on the blockchain or on the ledger, something changed on the data, and that created a new hash completely different from that.
Yeah, totally. And we don't necessarily have time to get into every detail about how everything on the blockchain works clearly. But I highly recommend people go check out more resources on like how a Merkle tree works. If you're not familiar with it already, it's very similar like how Git works. If you ever use source control with Git, like the Merkle root, and you're talking about, any changes in the hash being evidence that you don't have the same copy of the ledger or the same copy of the blockchain. Also, other analogies, like if you want more resources on, even just how cryptography in general works, there's lots of ways we use cryptography in the blockchain. Right now, we're talking about, transactions themselves. There's different hashing functions that we talk about, that are used in different ways in the blockchain. Basically, it's just a way to encrypt data or hide information. And that just basically means you can take a lot of different input and it's always going to have the same output. It's like a password in a database. That's how most of your modern databases work. When you store your password, it stores a hash of your password, right? And we're always comparing hashes. We're not comparing the password itself. And that's, really, that's another analogy that we can use to understand this, and try to give you all some more resources to go check out to understand some of the fundamentals of how, the cryptographic mechanisms on the blockchain work.
Right. And just a quick point that what you described, the password under the database and the hashes, that called like symmetric cryptography. What it means,
Right.
The input and the hash of the input should be the same. So if you want to access some information, both parties should have the same secret. And what blockchains uses like for signing transactions is called asymmetric cryptography. What that means that I have my private key, and with the private key, I have the public key. So,
Right.
And I can share easily my public key, and it will not give anyone access to my account because only my private key can unlock and spend the balance of my public key. So how does that work is that with a private key, it's like sort of your bank account check. If you didn't sign it, it's not going to work. If you wrote some information on your check, you put your signature in it with your private key, that's your signature. And that signature can be used to propagate to blockchain network, and the network will validate it's a valid signature because of the elliptic
curve.
Yeah, elliptic curve digital signature algorithm. It can be verified that this signature was originated from that public key without exposing your private key.
Right.
So anyone can verify this signature, and then they can basically process that transaction.
Yeah, totally. Yeah, I think that's a great point. And, kind of going back to the thing we talked about, the database, the passwords in the database, I mostly brought that example as just sort of like something that people might think about that they might have encountered before, right? If they're a developer, and mostly just kind of relating that to, here's a use case where you've probably used a hashing function in the past. We use different hashing functions in different places on different blockchains. Roman brought up a great point about the asymmetric cryptography, or we also call it public key cryptography. It's where we, get this idea of a public key and a private key. Your private key is kind of like your password on the blockchain, and your public key is kind of like your username. It's not a perfect analogy, but I've seen people get a lot out of that analogy. And yeah.
Mm-hmm. Yeah, I think that's a great analogy.
Cool. So I think that gives, we talked a little bit about the crypto side of cryptocurrency. So if all these blocks are, chained together by a block hash, right? Like we talk about all these transactions are bundles of records, the transactions are records, and they're bundled together in blocks, which are chained together. Let's talk a little bit about, why it's so hard to change the history of the blockchain. And I'll kind of kick us off with this. Like, part of what makes this really hard is that, when you build a blockchain, you basically start from somewhere. You start this idea of the Genesis block, and then you start adding transactions to that, and then they get contained into these blocks, which get chained together. And anytime you make a new block, basically what it is and correct me if I'm subtly wrong here, but basically what happens is you get a cryptographic representation of that block that is included in the next block. And then when you start adding blocks on that, because each block that you added is going to have each block that you add is going to have a cryptographic representation of the previous block and every block before that in the blockchain. And that is basically why it's going to be so hard to change the history of the blockchain, because if you want to make a new valid block, it has to have the encrypted version of the previous block, which also has the block before that, all the way back to the Genesis block. Is that a pretty good summary of the problem of changing history?
Yeah, pretty much. The thing that you have to consider too is that you don't do one transaction every 10 seconds or whatever. There's always going to be more transactions and more transactions added to the chain itself. And when you want to, create or alter a transaction that was already made before, you not only have to change that single transaction, you also have to change every other transaction after it before another transaction gets inputted into the chain. So it's really hard to change the previous history of the blockchain because of that, because you have such a short window of time to do a lot of processing work, to create all of those hashes, which do take some processing power. They're not like simple algorithms. They do take processing power to create those hashes. And you not only have to do that once, but you have to do that all of the times that you want to, for every single transaction from that point to now, before another transaction gets added,
Yep, I agree on that.
Yeah.
Yeah, totally. So where does that put us with our 51% attack problem? Maybe how can that bring us back to this thing that we've mentioned in the past? And now that people might have a little more understanding of how blockchains work, how we use cryptography on blockchains. So how does it make a 51% attack hard?
So in order to have a 50, so
what is a 51% attack, first of all?
Okay, so there are actually great already executed attacks, successful attacks with a 51% for some chains that are not very secured in terms of public trust. Why is that? Because there is not a lot of mining capacity that people target to, let's say, I think Ethereum Classic and some sort of Bitcoin forks, they've been already hacked and executed a double spend attack because miners, there is not enough miners to mine this cryptocurrency. So that's why the difficulty to create a new block much lower comparing to some more popular blockchains like Bitcoin and Ethereum. So if you want to execute a 51% on Bitcoin, you would have to have the hashing. So there is a term called like hashing difficulty right now. It means how many hashes per second you have to generate in order to be a competitive miner.
Right.
So what that means, what's the hashing per second? That means your computer, it can like execute just think about some function like you give some like random input and it produces some the hashed output. What that means, if that hash is valid, so what does it mean like valid hash to mine a block? It means there has to be some leading zeros in the beginning of this hash, and if there are enough like zeros, that means this hash could be valid and it could be accepted as a new block. Why is it so hard? The more zeros you have in the beginning, the harder it will be to find this random input that will produce this hash. So that's why like some blockchains, they don't have too much hashing power. So you can you can quickly spin up some infrastructure to get to that level of hashing power and to get to 51% of this hashing power. So you can look, it's all public information, so you can see who are the miners for some particular blockchain, and you can evaluate what's the current hashing power you have to have in order to execute it. So that means you can out-hash the current miners, so you can create blocks much faster than they are. That means you will gain the authority to create blocks. That means you will be able to create your own database.
You're basically saying that the computing power that you need to have, it needs to be greater than the computing power of the entire network, right?
Yes.
Or at least 51% of the network.
Yeah, at least 51%, because you can mine block faster than they are, and so you can produce the history. So they will not be able to present their block. Even if they do, you have your own 51%. You can reject their block, saying, no, we are the consensus right now. We are the miners who will agree on a new block, and we don't agree on any block that is not produced by me.
Yeah. So the thing about mining is that you're constantly creating hashes or finding new valid hashes, right? And you said that if they have zeros on the beginning, the more zeros they have, the more difficult it is to find. But like I said before, all those hashes, they are of fixed length, right? So doesn't that mean that you have a fixed number of possible hashes that you can create over time? I've seen people saying that blockchain is going to get like that. Bitcoin is going to have a Bitcoin 2.0. It's going to have a fork of Bitcoin itself, or should it not have a fork? Does that have something to do with the limited amount of hashes that you can create?
I don't know the answer to this question, to be honest. So what I've seen miners do is called like selfish mining. So they can already pre-mine some of the blocks because they know they already found the blocks, but they just didn't propagate this to the network. And when they essentially do that, they don't include any transactions into those blocks because they've been pre-mined ahead of time. That's a little bit disadvantage of proof of work consensus. And what are the possible things that can happen in proof of work? And of course, I want to jump into like proof of stake algorithm and why it's much more efficient and it's much faster, and why there are so many people are trying to build a scalable solutions for existing blockchains, because we already know the proof of work is not scalable in terms of transaction throughput and how much, and it also becomes sort of centralized as well, because it requires for every node to store the whole history of blockchain, which also proves us that it's not scalable. We, like Bitcoin and Ethereum networks, they became already so large so that like a simple laptop cannot just run the full node. It's just really expensive, and it takes a lot of storage and time just to synchronize the blockchain. So that's why there are multiple versions of how we can scale blockchains. For example, proof of stake is just to get rid of the extensive computation power, and sharding blockchain, that means so you don't have to store the full history of the blockchain, so you can just store some piece of this blockchain, and it's still, and the network can still exist with all of those connected shards.
Yeah. So, we talked a little bit about, proof of work, proof of stake. Just really quickly while we're here, maybe want to clarify, what these are. We talk about consensus algorithms or consensus mechanisms. Proof of work and proof of stake are examples of these. Maybe really quickly, we just call out kind of some of the popular blockchains, not necessarily everything, but kind of give examples of who's using proof of work, who's using proof of stake, who's trying to use proof of stake, and maybe fundamentally like what these things do.
So yeah, for sure. I know that I know a little bit about proof of work. I think that Roman will be able to explain more about proof of stake. But proof of work, it essentially started with Bitcoin. Bitcoin is the largest blockchain that I know that is using the proof of work algorithm. And you guys can correct me if I'm wrong, but basically how it works is that in order to have to input, sorry, in order to input a valid transaction on the network itself, you need to provide the computational power required for you to, provide a new hash. So what we were talking about mining is that the mining itself is, choosing and creating those random numbers and combinations of letters and numbers or characters to create a new hash that is a valid hash. So once you find a valid hash that hasn't already been stored on the blockchain itself, we do that with the zeros in advance to see which ones are new hashes or not. So once you find that new hash, you can input a transaction, or I don't know if it's a single transaction or multiple transactions, but you can basically say, okay, now that I found this new valid hash, I can say that this transaction is valid or not.
Yeah, exactly. And
that's what I understand of proof of work.
Yeah, and just clarifying like where the name comes from, like producing that valid result is the proof of your work as a miner.
Mm-hmm. Exactly. It's proving that you have the computational power, that you worked to get to that hash, that valid hash.
So that you get a reward in cryptocurrency.
Yeah, exactly. And in the case of Bitcoin, that reward is the coin itself. And there's a lot of like a lot of things that happen to get to that reward, and then after that reward happens, there's a lot of pooling, where people say, like you say, 50, 100, 500 people are working together as a single miner, so that when the reward comes, they split the reward in between themselves, and things like that.
Yeah, it's like a mining pool.
Yeah.
And besides just the reward, they also get to collect the transaction fees. That's why for users, it's a little bit crazy that at some periods of times the transaction fee could be really high, and sometimes it's just it's not that high. It depends how many pending transactions in a memory pool exist right now, and what's the market current rate that people are willing to pay to the miners to include their transactions. And then in blockchains like Bitcoin and Ethereum right now, the higher you specify the fee you're willing to pay, the more incentivized the miner will be to take your transaction into the next block.
Yeah, it's a simple supply and demand problem.
Yeah, correct. Yeah, exactly.
All right.
Which when you're thinking about blockchains, you're going to quickly start thinking about things in economic terms. It's, especially when you're dealing with blockchains that, use a currency like this. And a lot of these use cases, deal with financial transactions. Probably, I bet at some point we'll get into an episode where we talk about crypto economics a little bit. But yeah.
Yeah.
Okay, cool. So yeah, I think Roman, you want to tell us a little bit about kind of Ethereum's consensus mechanism right now, and maybe what it's looking to do in the future?
Sure. I think right now the most popular ones are delegated proof of stake. It basically means anyone can become a node with a minimum like staking power. What this staking power means is there is like a delegation and all right, let me get it started over. So you can run a node and propose to the network that I would like to be a validator. There, for some different delegated proof of stake algorithms, there could be a different minimum barrier to enter the network. So, for example, like in EOS, I believe in order to become a validator right now, you have to have like $10 million to just be a validator.
Wow.
Which is really high barrier to get in. But I think when they just started, the barrier were much, much lower.
Mm-hmm.
So anyway.
Sorry, but by validator, you mean someone that, says, oh, this transaction is valid or this transaction is not valid?
Yeah. No. So in this case, we don't have miners anymore.
Mm-hmm. Yeah, validator is a miner.
Yeah. Oh, okay. Right.
Yeah, validator produces the blocks. So let's say I would like to propose to be a validator, and then in order to increase my voting power, I can have, like, if you just have your like EOS currency, you can delegate that currency to the validator. So what that means, you increase the voting power of that validator, and the more voting power you have for some algorithms, the much more likely you will create a new block.
So basically how it works is some sort of election. You're saying that, you need to have a specific voting power so that,
right.
Other parties in the network, they vote for someone to be a validator, and that validator gets to say which transactions are valid or not. Is that it?
It's not just it gives them the power to create blocks and include those transactions into the block.
Oh, right. Okay. So they get to create the transactions and propagate them to the network.
They include the transactions and propagate to the network, yes.
Okay.
User transactions. So that's why it's called proof of stake, like how much stake has been delegated to a validator to make it a trustworthy validator. So if there is enough stake in a validator node, that means this validator is more likely to not to cheat to the network because he has too much stake.
Mm-hmm. Right.
So, and there are, like, Vitalik is trying to come up with a proof of stake algorithm. It's not like I want to make a huge difference between delegated proof of stake and proof of stake. With a proof of stake, that means anyone can become a validator. You don't have to, I don't think there is any like delegation process exists. So the way it works, you can only be a validator with your own stake. If I am not mistaken, because this is still kind of new thing to me, and I'm still trying to learn this stuff, so I might be wrong.
Aren't we all learning a lot of things when we're building with blockchains? Yeah, totally. And also, just for clarification, Roman, so that just to dispel any potential confusion, what are we using right now on Ethereum?
Right now, it's proof of work.
Right. Yeah, very cool. All right. So, guys. So really quickly, we're kind of getting to the end of our episode today. We talked mostly about public blockchains and cryptocurrency and how that works. And I think at some point we'll probably need to spin off into an episode where we talk a little bit more in detail about private blockchains. But maybe, Bruno, you want to give us a kind of quick contrast of a use case for private blockchains and how they might fundamentally work differently than a public blockchain?
Yeah, for sure. Like you said, private blockchains, they have a lot of things different. Like a lot of things work differently than public blockchains. But you also have protected blockchains. They're not necessarily private, but I think that's also something for another episode. How private blockchains work, it depends on your consensus algorithm, but the main reason for them to exist is that fear of, having all of your information public. So say for the use case of transactions and, bank transactions like we talked about, it's completely okay to have a public blockchain, maybe even better. But if you think about a business, say a mining company or, whatever kind of business, having all of your information to the general public, to general network, even your rivals, isn't something, interesting. It's not something you want to have. So the private blockchains, they work by having permissions into them. So it's not a blockchain that anyone can access. It's a blockchain that members of that company, for example, can access. A big example of that is what IBM is doing with Food Trust. They have a private blockchain to where the main purpose of it is not necessarily to validate transactions, but to tell you where some food is coming from. Say you go to a market and you see a packet of carrots, for example. With Food Trust, you can see the whole history that that specific carrot took. You can see in the packaging itself, there would be a label saying, okay, this was planted in this farm, then this truck got it from that farm and transported it to this market, which then sold it to the place that you are right now, and you're going to be the one to purchase it. So you can see all that history of what an asset has done, and it works a lot like the public blockchains on the cryptocurrency example that we were saying. But you don't necessarily have to have a coin to operate and transact. You can basically have anything of value, say anything like from a USB dongle to houses, or voting on your vote on an election, for example, or like we said on the previous episode, your medical records, they could also be something of value that you want to transact. So in the private blockchain, not everyone can access that blockchain. You need to ask permission, and it works a lot in the way of the hashing and the private and public keys. You also have that on the private blockchain, but it works to validate, okay, you have different groups of validators, right? You don't just have the groups of users or nodes or whatever you want to call them that are going to input the transactions, but you also have the users or members that are going to validate each other's users. You have a little bit more of segmentation into that. It's sort of like you have blockchains inside of blockchains. At least that's how it works on Hyperledger and those bigger private blockchains that I've been working with. So you basically have, the proof of stake algorithm, or what they call the PBFT algorithm, practical Byzantine fault tolerant algorithm, to decide, okay, which one of these members are going to be the orderer members that are going to order in which order the transactions are going to be made. And then we have the members that are going to decide which orderers are valid or are not valid. And then, you have all those segmentations, not just for the transactions, but for the members themselves, so that, you can control which member, what members can go through the network itself. And I think we can say that, go deeper into that in a future episode on private blockchains and how they work, and all of the concepts that they have. But they differ from public blockchains in that aspect of not anyone can access them. You need to have permission from other members of the network to tell you, okay, you're free to do these tasks. It's sort of like a user management system where you have the administrator, you have the common user, you have the permissions system in the private blockchain as well.
Yeah, totally. That makes perfect sense. Thanks for that explanation. And yeah, I think it,
Awesome.
definitely will make more sense to go in depth on some of these topics in another episode. Well, everybody, I think we're kind of getting to the end of our time for today. I've really enjoyed this chat. I think we've kind of gone in depth on a lot of topics about how the blockchain works. Thank you guys for those explanations.
Awesome. Thank you. It was really amazing, talking about the blockchains, and yeah, it's really great to have you guys here.
Yeah, totally. Well, I'm going to go ahead and wrap us up here. Everybody, thanks again for listening. This has been our second episode of Adventures in Blockchain. We've talked about how blockchain works. So stick around for the next episode, and we'll catch you then.
Bandwidth for this segment is provided by CacheFly, the world's fastest CDN.